All right, today we're going to tackle one of the most useful ideas in all of science, the Beer-Lambert law. Now, I know it sounds a little intimidating, but I promise by the end of this, you'll see it's actually super intuitive. So let's start with a puzzle. How on earth can a simple beam of light act like a super precise chemical detector? How can it tell us not just what's in a solution, but exactly how much of it is in there? Well, that's the big secret we're going to unlock today. Okay, first things first, let's get down to the basic idea. At its heart, this whole law is about something you probably already get without even thinking about it. The link between how much stuff is dissolved in something and, well, how dark it looks. Think about it like this. You're making a cup of tea. If you just dip the tea bag in for a second, you get this weak, light-colored tea, right? You can see right through it. Way more light is passing through. But if you let that thing steep for like 10 minutes, it gets super dark and intense. It's more concentrated, and way less light can make it through. That simple observation is the foundation for this entire thing. So how do we go from a simple cup of tea to a full-blown scientific law? Well, it didn't just pop out of nowhere. It was actually built on two key pillars, two totally separate discoveries that, when put together, created something way more powerful. So here's the game plan. First, we'll look at what a guy named Lambert figured out about distance. Then we'll bring in another scientist, Beer, who was focused on the concentration part. And then we'll see how these two ideas snap together perfectly to give us the Beer-Lambert law. Lambert's law came first, way back in the 1700s. And what he figured out was this. The farther light has to travel through something, the more of it gets soaked up. Just imagine you're looking through one pane of stained glass. Now imagine looking through 10 of them stacked together. That stack of 10 is going to look way darker, right? Well, that's Lambert's law. The thickness, or what scientists call the path length, really matters. So then, about 100 years later, Beer adds the final piece to the puzzle. He realized that the exact same thing Lambert saw with thickness was also true for concentration. The more concentrated your solution is, the more light it blocks. And that takes us right back to our cup of tea, doesn't it? The stronger the tea, the less light gets through. Simple as that. And when you smash those two ideas together, Lambert's path length and Beer's concentration, you get this beautiful, simple, and incredibly powerful equation. This is the hero of our story, the Beer-Lambert law. A equals epsilon CL. It looks so clean because the ideas behind it are just as clear. Let's quickly break this down. A is for absorbance. That's just a number for how much light gets blocked. L is the path length from Lambert, basically how wide the container is. And C is the concentration from Beer, how strong our tea is. So what about that weird Greek letter, epsilon? That's the secret sauce. Think of it as a unique fingerprint for a chemical. Every substance absorbs light a little differently, and this number captures that unique property. It's what makes the whole thing work.
Okay, so this equation is great and all, but how do scientists actually use it? How does it go from a theory on a page to a tool that gets real work done in a lab? This is where it gets really cool.
They use a machine called a spectrophotometer. You can think of it as the engine that runs on the Beer-Lambert law. It does something really simple. It shines a very specific color of light from a source, sends it through your sample, which is in a little container called a cuvette, and then a detector on the other side measures exactly how much light made it out. By comparing the before and after light, it calculates the absorbance, our A value. So you've got this absorbance number. What now? Well, to make it useful, scientists first have to create a kind of map. It's called a calibration curve. They take a few samples where they already know the exact concentration, measure the absorbance for each one, and then plot those points on a graph. And this graph, the calibration curve, is the secret weapon. You'll notice it's a perfectly straight line. That's the Beer-Lambert law staring right back at you. You've got absorbance going up the side and concentration along the bottom. Once you have this map, you can take your mystery sample, measure its absorbance, find that number on the side, just trace your finger over to the line, and then drop straight down, and boom, that's your exact concentration. So really, the whole process just boils down to a simple two-step dance. You measure how much light is blocked, and then you use this graph to instantly translate that number into a precise concentration. It's an incredibly powerful trick used in labs all over the world every single day. But you know how it is in science. No model is ever perfect. It works brilliantly under the right conditions. So it's really important to know where the limits are. Time for a quick reality check. This pretty much says it all. On the left, you've got the dream, the perfect, straight line that the equation promises us. But on the right, well, that's what can happen in the real world. At higher concentrations, that beautiful straight line can start to bend. The simple relationship starts to fall apart. So, why does it go off the rails? Well, there are a few culprits. The biggest one is just that the law is really designed for dilute or weak solutions. When things get too concentrated, the molecules start bumping into each other and messing with how they absorb light. Other little things like stray light hitting the detector by accident or even changes in temperature can also throw the whole measurement off. And that brings us to the real bottom line. Even with these limits, the Beer-Lambert law is an absolute cornerstone of science. Its real power is in quickly and accurately figuring out concentrations, especially in those dilute solutions where it works like a charm. So we've seen how a simple beam of light, guided by this really elegant law, can literally make the invisible visible. It lets us measure what's hidden in plain sight. It kind of makes you wonder, doesn't it? We have this amazing tool to measure the things we know are there. What else could we discover if we just found the right way to look? What other invisible things could we measure next?